Hello learners, welcome to the third session of Linear Algebra. Myself, Gayatri P., an Assistant Professor of Mathematics working at Government First Grade College, Sulya, Dakshina, Kannada. Learning Objectives. Learners, in this session, we learn about the system of non-homogeneous linear equations and minimum polynomial of a matrix. Learning outcomes. At the end of this session, you will be able to find the solution to the system of non-homogeneous linear equations and to find the minimum polynomial of a matrix to determine the non-singularity of that matrix. Students, now we study about system of non-homogeneous linear equations. Definition: a system of linear equations of the form a11x1 plus a12x2 plus etc. plus a1n xn equal to b1, a21x1 plus a22x2 plus etc. plus a2n xn equal to b2. Continuing in this way, mth equation am1x1 plus am2x2 plus etc. plus amn xn equal to bm, where aij bi in F is called a system of non-homogeneous linear equations. This system can also be written as sigma j equal to 1 to n aij xj equal to bi for every I 1 less than or equal to I less than or equal to m. Students, here we have a problem to show that the system of non-homogeneous linear equations x1 minus 2x2 plus x3 equal to half, 2x1 minus 5x2 plus 2x3 equal to 1, x1 plus x2 plus x3 equal to 1 has no solution. Solution: if x1 equal to c1, x2 equal to c2, x3 equal to c3 is a solution, then we substitute these values, that is x1 equal to c1, x2 equal to c2, x3 equal to c3 in this system of equations. We get three new equations: c1 minus 2c2 plus c3 equal to half, that is this one, that is equation number 1. 2c1 minus 5c2 plus 2c3 equal to 1, that is equation number 2. c1 plus c2 plus c3 equal to 1, that is equation number 3. Now, equation 2 minus 2 times equation 1 gives, that is equation 2 is here, 2 times equation 1 is here. So we have equation 2 minus equation 2 times equation 1, we get as 2c1 minus 2c1 cancels, minus 5c2 minus of minus plus 4c2, so that is minus c2. 2c3 minus 2c3 cancels, 1 minus 1 is 0. So here we get minus c2 equal to 0, therefore c2 equal to 0. Next, equation 3 minus equation 1 gives, here see equation 3 is here, we subtract equation 1, that is here. So c1 minus c1 cancels with each other. c2 minus of minus 2c2 is 3c2 and c3 minus c3 cancels, 1 minus half is half. So we have 3c2 equal to half. By cross multiplying, c2 equal to 1 by 6. Students, here we notice that there are two values for c2, one is 0 and other one is 1 by 6. These two values are inconsistent. Therefore, the system of equation has no solution. Students, here is a note for you. Given the system of non-homogeneous linear equations, sigma j equal to 1 to n aij xj equal to bi for every I 1 less than or equal to I less than or equal to m. The associated matrix A equal to the matrix Aij, that is the matrix A11, A12, etc. A1n, A21, A22, etc. A2n, M through AM1, AM2, etc. AMN. This is an M by N matrix and this contains Mn elements. Now, the augmented matrix A dash of this system is also denoted by like this, that is matrix A comma B is the matrix A11, A12, etc. A1n, B1, A21, A22, etc. A2n, B2, AM1, AM2, etc. AMN, BM. Students, this is an M by N plus 1 matrix. Here we note that the first N columns are the same as the first all the columns of associated matrix, and the last column is made up of constants B1, B2, etc. Bm. Now we have a proposition. The system of non-homogeneous linear equations sigma j equal to 1 to n aij xj equal to bi for every I 1 less than or equal to I less than or equal to m, where aij bi are scalars, has a solution if and only if rank of the associated matrix A equal to rank of the augmented matrix A dash. Students, here is a proposition for you to prove. A system of n non-homogeneous linear equations in n unknowns has a unique solution if and only if associated matrix is non-singular. To prove this, let sigma j equal to 1 to n aij xj equal to bi 1 less than or equal to I less than or equal to n be the system of equations with the A equal to aij as the associated matrix. Here, students, here we note that there are n unknowns x1, x2, xn in n equations. Here see 1 less than or equal to I less than or equal to n means there are n equations. And we know that if the associated matrix, that is A, is non-singular, then the rank of that matrix equal to n, the number of linearly independent rows or columns. The augmented matrix A dash is an n by n plus 1 matrix here, and hence its rank cannot be greater than n because the first n columns of the augmented matrix A dash are linearly independent. Therefore, rank of the augmented matrix A dash equal to rank of the associated matrix A, that is equal to n. Hence, the system has a solution and is unique because the associated homogeneous equation sigma j equal to 1 to n aij xj equal to 0, 1 less than or equal to I less than or equal to n has only a trivial solution. That is a solution. We know that C1 equal to 0, C2 equal to 0, etc. Cn equal to 0. To prove the converse, conversely assume that the system has a unique solution. Then the corresponding homogeneous system, sigma j equal to 1 to n aij xj equal to 0, 1 less than or equal to I less than or equal to n has only a trivial solution. This implies that rank of A is equal to n and therefore A is non-singular. Students, here is a problem to solve the system of non-homogeneous linear equations x1 minus 2x2 plus x3 equal to 1, 2x1 minus 5x2 plus 2x3 equal to 2, x1 plus x2 minus x3 equal to minus 1. Does it have a unique solution? Why? Solution to this problem. Students, we know that Ax equal to B, where A is the associated matrix associated with this system, that is 1 minus 2 1, 2 minus 5 2, 1 1 minus 1 obtained from the left hand side of these three equations, that is coefficients 1 minus 2 1 here, 2 minus 5 2, that is the second row, 1 1 minus 1 from the third equation, that is the third row. So also x means the column matrix x1 x2 x3 of unknowns and B is the constant matrix 1 2 minus 1, that is obtained from here 1 2 minus 1. This is the matrix of constants. Then we can write the matrix of unknowns, that is x equal to A inverse into B. Now to find out the unknowns, we have to find A inverse into B. For that, we first find out what is A inverse using elementary row operations. To find A inverse, I have written A on the left hand side and I3, the identity matrix of order 3 on the right hand side. Now we perform two elementary row operations, so we change these 2 and 1 as zeros. For that, first we perform the elementary row operation P21 of minus 2. That means we change the second row by multiplying the first row by minus 2 and add it to the second row. So we get the new elements of second row, that is by after performing the elementary row operation P21 of minus 2. Already we studied about this. So we get these new elements as 0, minus 1, 0, minus 2, 1, 0 instead of 2, minus 5, 2, 0, 1, 0. See here. Next, we perform the another elementary row operation, that is to change here. We have to make 0. So P31 of minus 1, that is we multiply the first row by minus 1 and add this to third row so as to get the new elements as 0, 3, minus 2, minus 1, 0, 1 instead of 1, 1 minus 1, 0, 0, 1. See, so here see first column becomes the first column of the identity matrix. Here see 1 to 1, here 1, 0, 0 changed. Okay, next we perform the two elementary row operations simultaneously, that is P1 2 of minus 2. That is we have to change the, here see minus 2, we have to change the second element of the first row, that is to 0, and P3 2 of 3, that means we have to change the second element of third row as 0. So we perform these two row operations. Now P1 of 2 minus 2, that is performing this elementary row operation, we get the first row as 1 0 1 5 minus 2 0 instead of 1 minus 2 1 1 0 0. And again we perform P3 2 of 3 so that we get the new third row, that is 0 0 minus 2 minus 7 3 1 instead of 0 3 minus 2 minus 1 0 1. Next, we see that here we have to change this element, that is the third element of the first row as 0. So as to get this, and we change this also. Here is a minus 1, we need plus 1 so that this becomes second column of the identity matrix. So we perform the two elementary row operations. First one is P1 3 of 1 by 2, that is multiply the third row by 1 by 2 and add it to the first row so that first row will get changed. So here we perform the elementary row operation on this third row multiplied by 1 by 2 and add it to the first row to get new elements 1 0 0. Here see, here 1, here it is 0 changed. Simultaneously this 5 minus 2 0 changed to 3 by 2 minus 1 by 2 1 by 2. Again we have to make this minus 1 as plus 1. So we multiply all the elements of second row by minus 1. So we get 0 1 0 2 minus 1 0. Second row, see here only changes its sign. Now finally we have, see here only here the second column changes to the second column of the identity matrix. Only here we need plus 1. So we make the perform the elementary row operation M3 of minus half, that is multiply the third row by minus half so as to get the third element of third row of the associated matrix as 1. So we get the new matrix as 1 0 0. Here see 3 by 2 minus 1 by 2 1 by 2 0 1 0 2 minus 1 0 0 0 1. This is obtained by multiplying by minus 1 by 2 here. Here we multiplied, so we get plus 1. Multiplying minus 7 with minus 1 by 2, we get this 7 by 2. And multiplying 3 into 3 and minus 1 by 2, we get minus 3 by 2. And 1 into minus 1 by 2 is minus 1 by 2. So see the last row. Here we see that A is converted as an identity matrix, that is I3, and simultaneously the identity matrix I3 converted to A inverse. Hence A inverse equal to 3 by 2 minus 1 by 2 1 by 2 minus 2 1 0 7 by 2 minus 3 by 2 minus 1 by 2. A inverse exists means A is non-singular. This shows that A is non-singular, and non-singular A inverse exists and is not A is non-singular means the solution is unique, that we know by the previous proposition. And unique solution is X equal to A inverse B, that is here A inverse multiplied with the column matrix, that is B. So here we multiply 3 by 2 into 1 plus minus 1 by 2 into 2 plus 1 by 2 into minus 1 gives 0. Minus 2 into 1 plus 1 into 2 plus 0 into minus 1, that is equal to 0. 7 by 2 into 1 plus minus 3 by 2 into 2 plus minus 1 by 2 into minus 1 gives 1. So we get the three values as x1 equal to 0, x2 equal to 0, x3 equal to 1. This is the unique solution of the given system of equations. Students, here we prove the proposition, let F be a field and let A belongs to Mn of f, then there exists a non-trivial polynomial f of x in f of x such that f of the matrix A equal to 0. Here Mn of f means the vector space of all matrices of order n over the field f, and f of x means it is the vector space of all polynomials over the field f. We have to show that if f of x is a polynomial, if we put x equal to the matrix A, then we will get the 0 matrix. That is, we have to prove. So now proof, see here, proof. Students, we know that Mn of f is a vector space of dimension n square. That means the number of basis elements of this Mn of f is n square. That is the maximum linearly independent set. That means there are n square elements which are linearly independent. So if we just add one element to these n square elements, then that n square plus 1 elements will become linearly dependent. In particular, we take I, the identity matrix, In, A square, etc., A power n square. So there are n square plus 1 elements of Mn of f. These are linearly dependent. Students, we know that linearly dependent means we can find a non-trivial linear relation between these n square plus 1 elements. Therefore, see here, there exist scalars a0, a1, a2 up to an square in f, not all zeros such that a0 I plus a1a plus a2a square, etc. an square, a power n square equal to 0. See here, if we replace this a by x, I by 1, we get f of x as a0 plus a1x plus a2x square, etc. an square x power n square. So we take this as f of x. So if we put x equal to a, that will be 0. So hence the result, see here. Hence, f of x equal to sigma I equal to 0 to n square ai x power I is the required polynomial with f of a. See here, instead of x we put a, then we will get this. So that is the 0 matrix. So f of a equal to sigma I equal to 0 to n square ai a power I is 0. Hence, we proved this proposition. Students, now we learn about minimum polynomial of a matrix. Definition: a polynomial f of x of least degree and with highest degree coefficient equal to 1 such that f of a equal to 0 is called a minimum polynomial of matrix A. Here is an example. To find the minimum polynomial of the matrix A equal to 1, 1, 1 minus 1. Clearly A is a non-zero matrix. So here we find out A square. See, A square is equal to A into A. So we multiply A into A using matrix multiplication to get here 2, 0, 0, 2. That is here 1 into 1 plus 1 into 1, that is 2. 1 into 1 plus 1 into minus 1, that is 0. 1 into 1 plus minus 1 into 1, that is 0. 1 into 1 plus minus 1 into minus 1, that is 2. So we get the matrix A square as 2, 0, 0, 2. Now this can be written as 2 is taken outside, 2 times 1, 0, 0, 1, that is 2 into identity matrix of order 2 or 2 by 2. Okay. Next we take this 2i to left hand side to get a square 2i equal to 0, where 0 is the 0 matrix. Now if we put a equal to x and I equal to 1, we get the minimum polynomial. So see here, a satisfies the polynomial x square minus 2 and coefficient of x square is 1. Therefore, f of x equal to x square minus 2 is the minimum polynomial of a. Students, here is a proposition for you. Statement: let A belongs to Mn of f and let Q of x belongs to f of x, a minimum polynomial of A. If f of x belongs to f of x is any other polynomial satisfied by A, then Q of x divides f of x. Students, here A is an n by n square matrix elements from the field F. Here Q of x is the minimum polynomial of A, so Q of A is 0. F of x is any other polynomial satisfied by A means f of A also 0. We have to prove Q of x divides f of x. Here we use the property of the Euclidean domain for the Euclidean domain f of x. So proof is like this. Students, we know that f of x is a Euclidean domain. So by the property, that is third property of the Euclidean domain, f of x can be written as f of x equal to q of x into g of x plus r of x, where either this r of x equal to 0 or degree of r of x is strictly less than degree of q of x. Now, we substitute x equal to a in this equation to get f of a is equal to q of a into g of a plus r of a, that is equation number 1. Now we substitute f of a equal to 0, q of a equal to 0 in this equation to get here 0 equal to 0 plus r of a, that is r of a equal to 0. Now r of a equal to 0 means r of x must be equal to 0, otherwise it will become a minimum polynomial, contradiction to the fact that q of x is a minimum polynomial of a. See here. Hence r of x equal to 0, since degree of r of x is strictly less than degree of q of x and q of x is the minimum polynomial of a. Now r of x equal to 0, this gives here f of x equal to q of x into g of x. See here. So f of x is q of x into g of x. That implies by the property of division, q of x divides f of x. Corollary to the previous proposition. The minimum polynomial of the matrix A is unique. Students, here we have to prove that if there are two minimum polynomials, then they are equal. Proof. Let q1 of x and q2 of x be two minimum polynomials of matrix A. Since q1 of A equal to 0, that means A satisfies the polynomial q1 of x, and we consider q2 of x as a minimum polynomial of A, then by the previous proposition we get q2 of x divides q1 of x. Similarly, we can show that q1 of x divides q2 of x. That is, if we take Q2 of A equal to 0 and consider Q1 of X as a minimum polynomial of A, then we get Q1 of X divides Q2 of X. So, here we have two results. Q2 of X divides Q1 of X and Q1 of X divides Q2 of X. So, we can write Q1 of X is equal to A times Q2 of X, where A is a non-zero scalar. That is by property of polynomial. Here we know that f of x is an Euclidean domain also. But both Q1 of x and Q2 of x have the highest degree coefficient equal to 1 because they both are minimum polynomials. Therefore, here we have in this equation A must be equal to 1. So, we get therefore Q1 of x equal to Q2 of x. So, the minimum polynomial of any matrix is unique. Students, now we prove the proposition let A belongs to Mn of f with Q of x equal to A0 plus A1x plus A2x power 2 plus etc. plus m minus 1 x power m minus 1 plus x power m as the minimum polynomial of A. Then A is non-singular if and only if A0 not equal to 0. Here see, hypothesis is given as Q of x is a minimum polynomial of A. We have to show that if A is non-singular, then A0 is non-zero. If A0 is non-zero, then we have to show that the matrix A is non-singular matrix. To prove this proof, suppose we take A0 is not equal to 0. That we take this, we show that A is non-singular. That means inverse of A exists. For that, here see, we use the hypothesis since Q of A equal to 0 because Q of A is 0 because Q of x is the minimum polynomial of A. So, A satisfies this polynomial. That means Q of A is 0. We have substitute here A0 plus A1A plus A2A square etc. Last term A power m that is equal to 0 because of this. Okay. Next, then we can write I as. See here, A0I can be written as minus of all these elements. Then I can be written as minus 1 by A0 of A1A plus A2A square plus etc. Last term A power m. So, next we write, take this A from all the terms. Here A is there, here A square, last term A power m. So, take one A common, that is taken outside to get I as minus 1 by A0, A1I plus A2A etc. plus A power m minus 1 into A. So, here see the product of the matrix A together with this matrix is the identity matrix I or IN. So, if we know that the result, if the product of two matrices equal to identity matrix, then they are inverses each other. So, we have inverse of A is here minus 1 by A0, A1I plus A2A etc. A power m minus 1. Here this is on the left hand side, so this is left inverse. So similarly we find out, take A onto the left hand side, so we get the right inverse of A. See here, similarly we can write I equal to, here we take a on the left hand side, a into minus 1 by a naught a1i plus a2a up to a power m minus 1. So this is the right inverse of a. So hence a is non-singular with a inverse equal to minus 1 by a naught of a1i plus a2a etc. a power m minus 1. So we have proved that if a naught not equal to 0, then a is non-singular. So one part of the theorem is proved. Students, here we prove the proposition, let F be a field and let A belongs to Mn of F, then there exists a non-trivial polynomial f of x in f of x such that f of the matrix A equal to 0. Here Mn of F means the vector space of all matrices of order n over the field F, and f of x means it is the vector space of all polynomials over the field F. We have to show that if f of x is a polynomial, if we put x equal to the matrix A, then we will get the 0 matrix. That is, we have to prove. So now proof, see here, proof. Students, we know that Mn of F is a vector space of dimension n square. That means the number of basis elements of this Mn of F is n square. That is the maximum linearly independent set. That means there are n square elements which are linearly independent. So if we just add one element to these n square elements, then that n square plus 1 elements will become linearly dependent. In particular, we take I, the identity matrix, In, A square, etc., A power n square. So there are n square plus 1 elements of Mn of F. These are linearly dependent. Students, we know that linearly dependent means we can find a non-trivial linear relation between these n square plus 1 elements. Therefore, see here, there exist scalars a0, a1, a2 up to an square in F, not all zeros such that a0i plus a1a plus a2a square etc. an square a power n square equal to 0. See here, if we replace this a by x, I by 1, we get f of x as a0 plus a1x plus a2x square etc. an square x power n square. So we take this as f of x. So if we put x equal to a, that will be 0. So hence the result, see here. Hence, f of x equal to sigma I equal to 0 to n square ai x power I is the required. Students, here is a proposition for you to prove. A system of n non-homogeneous linear equations in n unknowns has a unique solution if and only if associated matrix is non-singular. To prove this, let sigma j equal to 1 to n aij xj equal to bi 1 less than or equal to I less than or equal to n be the system of equations with the A equal to aij as the associated matrix. Here, students, here we note that there are n unknowns x1, x2, xn in n equations. Here see 1 less than or equal to I less than or equal to n means there are n equations. And we know that if the associated matrix, that is A, is non-singular, then the rank of that matrix equal to n, the number of linearly independent rows or columns. The augmented matrix A dash is an n by n plus 1 matrix here, and hence its rank cannot be greater than n because the first n columns of the augmented matrix A dash are linearly independent. Therefore, rank of the augmented matrix A dash equal to rank of the associated matrix A, that is equal to n. Hence, the system has a solution and is unique because the associated homogeneous equation sigma j equal to 1 to n aij xj equal to 0, 1 less than or equal to I less than or equal to n has only a trivial solution. That is a solution. Students, here is a problem for you to find the minimum polynomial of a non-zero. First one, nilpotent matrix. Second one, idempotent matrix. Now we find the minimum polynomial of a non-zero nilpotent matrix. See, by definition, a matrix A is a nilpotent matrix if A power m equal to 0 and A power m minus 1 not equal to 0. See here, A power m equal to 0 gives the minimum polynomial as x power m. So we have the result. Hence, minimum polynomial is f of x equal to x power m. Now we find the minimum polynomial of a non-zero idempotent matrix. By definition of an idempotent matrix, a matrix A is an idempotent matrix if A square is equal to A, then A square minus A is the zero matrix. That is, see here, A square minus A is equal to 0, the zero matrix. Hence, the minimum polynomial is f of x equal to x square minus x. Here see, put instead of a, put x. So, x square minus x. So, we can write this also by simplifying, taking x outside. F of x equal to x into x minus 1. Students, here we have a problem to find the minimum polynomial of the matrix 0, 0, 0, 1, 0, minus 9, 0, 1, 6. Find also its inverse if it is non-singular. Solution. Let A is equal to the matrix 0, 0, 0, 1, 0, minus 9, 0, 1, 6. First we find out A square. That is, A square is equal to A into A. So, here we multiply A twice using matrix multiplication. Here we see the first row of the A square is, matrix A square is 0. That is obtained by the first row of the matrix A is 0. So, we obtain the first row of the matrix A square is also as 0. Now we find the second row of A square as 0 minus 9 minus 54. For that, see here, 1 into 0 plus 0 into 1 plus minus 9 into 0, that is 0. Next, 1 into 0 plus 0 into 0 plus minus 9 into 1, that is minus 9. 1 into 0 plus 0 into minus 9 plus minus 9 into 6, that is minus 54. Similarly, we can find the third row of the matrix A square. That is 0 into 0 plus 1 into 1 plus 6 into 0, that is 1. 0 into 0 plus 1 into 0 plus 6 into 1, that is 6. 0 into 0 plus 1 into minus 9 plus 6 into 6, that is 36. So 36 minus 9 is 27. So we got the matrix A square as like this. Now we find out both 6a and 9i. We have 6a is obtained by multiplying all the elements of a by 6. So 6a we got as 0, 0, 0, 6, 0 minus 54, 0, 6, 36 from this a by multiplying all the elements by 6. Next we have 9i is equal to 9 times the identity matrix 1 0 0 0 1 0 0 0 1, that is 9 0 0 0 9 0 0 0 9. And unique solution is x equal to A inverse B, that is here A inverse multiplied with the column matrix, that is B. So here we multiply 3 by 2 into 1 plus minus 1 by 2 into 2 plus 1 by 2 into minus 1 gives 0. Minus 2 into 1 plus 1 into 2 plus 0 into minus 1, that is equal to 0. 7 by 2 into 1 plus minus 3 by 2 into 2 plus minus 1 by 2 into minus 1 gives 1. So we get the three values as x1 equal to 0, x2 equal to 0, x3 equal to 1. This is the unique solution of the given system of equations. Students, here we have a proposition to prove. That is, two similar matrices have the same minimum polynomial. Proof. Let A, B belongs to Mn of f be two similar matrices so that by definition B equal to CAC inverse where C is non-singular. And let Q of x equal to a naught plus a1x plus a2x square etc. last term x power m ai in f be a minimum polynomial of A. Here Q of x is a minimum polynomial of matrix A implies Q of A must be equal to 0. Therefore, see here, then Q of A is equal to A naught I plus A1A plus A2A square etc. last term A power m that is equal to 0 by definition of minimum polynomial of A. Here see, 1 is replaced by I and x replaced by A, x square replaced by A square and so on. Now we find out what is Q of B. Q of B is equal to Q of CAC inverse. Here B equal to CAC inverse. So, and we can write this Q of CAC inverse as A naught I. See here, compare here A, here CAC inverse. So A is replaced by CAC inverse here. So A square is replaced by CAC inverse whole square. Last term plus CA C inverse whole power m that is replaced by this A power m. And now we show that Q of B is also equal to the 0 matrix. For that, first term we have rewritten as A naught into CIC inverse plus second term A1 into CAC inverse plus third term A2 into CA square C inverse plus etc. Last term C into A power m C inverse. This is obtained by the result, that is for any elements of a group G, we can write AB A inverse whole power n is equal to A times B power n A inverse. Here we notice that C is a non-singular matrix and C inverse is also a matrix and A is an n by n matrix. So here Mn of F is a vector space over the field F. Therefore, it is also a group. So, we use this result to write CAC inverse whole square as C into A square C inverse, CAC inverse whole power m as C into A power m C inverse and so on. So, we get here C into A naught I C inverse plus C into A1 A C inverse etc. C into A power m C inverse by taking A naught inside. So that is equal to C times C is taken on the left hand side and C inverse on the right hand side outside. We get C times A naught I plus A1A plus A2A square plus etc. plus A power m. This is our Q of A. So here we put 0. So we get C into 0 matrix into C inverse. So that is equal to 0. See here, that is equal to C into QA into C inverse. That is 0 because Q of A is 0. So we have Q of B equal to 0 implies B satisfies the polynomial Q of X. Therefore, if P of X is the minimum polynomial of B, then clearly P of X divides Q of X. That is we know by the previous proposition. So, that is the equation number 1. Next, also we have P of B equal to, here B is same as CAC inverse. So P of CAC inverse we can write using this result. Q of B is C into Q of A C inverse. Here see. So P of B is C into P of A into C inverse. That implies here P of B equal to 0 because P of X is a minimum polynomial of B. So here we put 0. So 0 is equal to C into P of A C inverse. That implies P of A equals 0 because C and C inverse are non-zero matrices. Now P of A equal to 0 implies A satisfies the polynomial P of x. Therefore, Q of x, the minimum polynomial of A, divides P of x, that is equation number 2. Hence, we get P of x equal to Q of x because both P of x and Q of x have highest degree coefficient equal to 1. Hence, we proved the proposition. Students, here is an assignment for you. Problem A. Find the minimum polynomial of the matrix A equal to 0, 0, 0, 1, 0, 0, 1, 1, 0. Hint is given. The product of the matrices A cube equal to 0 and therefore f of x equal to x cube is the minimum polynomial of the matrix A. Problem B. Find the minimum polynomial of the matrix 2, 1, minus 1, 3, 4, 2, 0, 0, 1. Find also its inverse if it is non-singular. Hint. We have a cube minus 7a square plus 11a minus 5i equals 0. Here I means the identity matrix of order 3. Minimum polynomial is f of x equal to x cube minus 7x square plus 11x minus 5. Here we notice that the minimum polynomial has a constant term a0 equal to minus 5 which is non-zero. Therefore, the matrix A is non-singular. And A inverse equal to 1 by 5 of 11 into identity matrix I minus 7a plus a square, that is equal to 1 by 5 of 4 minus 1 6 minus 3 2 minus 7 0 0 5. Students, I hope all of you understood and enjoyed this part of the lesson. Thank you all. Thank you.